You just asked an AI a question, and 1 second later, it answered. But what happened in that 1 second? Hello everyone, welcome to my channel. Today we are going to pull back the curtains completely. We are going to understand each and every step that happens from the moment you press enter to the moment the first word appears on the screen, and why each step matters. This is the foundation video. Everything else in this playlist builds on what we discussed today in this video. So let's go. First, let's define the word inference. In machine learning, there are two phases, training and inference. Training is when the model learns. You feed it massive amount of text like books, website code, articles, and it adjusts billions of internal numbers called weights until it gets good at predicting what comes next. Training is expensive. It takes weeks and it is only done once, as it costs billions of dollars. Inference is when the model is used, the weights are frozen, and no more learning happens. You give it an input, it produces an output. This is what happens every time you use ChatGPT, Claude, or Gemini. And here's what people don't realize. Inference isn't just a technical problem. It's a massive business problem. Look at this OpenAI's 2025 estimated compute spend. Roughly $14 billion in total, and 62% of that goes to inference, not training, inference. Anthropic also spent an estimated $6.8 billion on compute in 2025. 60% of that also inference. Jensen Huang, CEO of NVIDIA, made a prediction that AI inference will be 1 billion larger than today. Inference has a tremendous business value at stake and continues to grow in importance. Think about what that means. OpenAI's inference cost is in 2025 nearly equaled their total revenue, contributing to an estimated $8.5 billion to $9 annual cash burn. Anthropic's inference spend came in 23% over internal forecast, which forced a downward revision of projected gross margin from 50% all the way down to 40%. And it's getting worse. The newest models that think before they answer, consume up to 150 times more compute than standard LLM for the same query. That is why inference optimization isn't just an academic. Every technique we cover in this series directly affects how much it costs to run an AI company. Faster inference means lower cost, higher margins, and the ability to serve more users. This playlist entirely focuses on inference, how to make it fast, scalable, and cheap. Now moving to the first thing, before the model can process your text, it needs to be converted into the number. This is called tokenization. Tokenization basically splits your text into chunks called tokens. Token is roughly 3 to 4 or on average, not exactly words, not exactly letters. Common words like the or is are single tokens. Rare words get split into multiple tokens. Like unbelievable in this image might be believe, able. Each token gets assigned a unique integer ID from the model's vocabulary. Like ChatGPT 4's vocabulary has around 100,000 tokens. Llama 3 uses about 128,000 tokens. So your message or this word like unbelievable becomes something like this. Just a list of integers that what goes into the model. Why does this matter? Because the number of token directly determines computational cost. A 1,000 token prompt costs roughly 1,000 times more to process than a single token prompt. This is why LLM's API charged by the tokens, not by the words. Next, the model doesn't work directly with integer IDs. It needs rich, continuous representation. The first thing the model does is look up each token ID in the embedding table. A giant matrix where each row corresponds to one token and each row is a vector of numbers, typically 4096 or a dimension for larger model. Think of it like a dictionary, but instead of word definition, each entry is a point in 4000 dimensional mathematical space, encoding the token's meaning. After embedding, each token is now a vector, and a sequence of token become a matrix of shape 10,4096. We also add positional encoding as we discussed in previous videos as well at this stage. The same reason, a way of telling the model where each token appears in the sequence. Otherwise, the model can't tell the difference between dog bites man or man bites dog. Then next, the main process starts where the real computation begins. The embedded matrix flows through the transformer layer, Llama 370 billion has 80 layers. Each layer has two components, self-attention and feed-forward neural network. In self-attention, this is where every token looks at every other token and asks, how relevant are you right now to me? We have covered this in depth in coming videos. The short version is like each token becomes a query, a key and a value, and queries match against keys to compute attention scores. Those scores weight the values. Each token gets a new context aware representation. So we have discussed this in our previous videos like LLM, coding LLM from scratch. I will link down that in the description. You can give it a go if you want to see it in depth. We will also discuss that in our coming videos as well. So, and in the feed forward neural network, after attention, each token's representation passes through a small neural network independently. This is where the model's knowledge lives. Facts, reasoning patterns, language understanding. The fast forward neural network is typically 4 times wider than the attention layer. A single transformer layer has attention, add and normalization, feed forward, add and normalization, as discussed in the previous video as well. You repeat this 80 times for the Llama 370 billion model. Each repetition refines the representation further. At the very end, you have a final representation for the last token in the sequence. This is the vector the model will use to predict the next token. Then after all 80 layers, the last token's hidden state is a single vector of 4096 numbers. This vector gets multiplied by the language model head, essentially the reverse of embedding table, producing a vector of 128,000 tokens or numbers. One for each token in the vocabulary. These are called logits. Higher logits equal to model thinks this token is more likely next. Then we apply softmax to convert logits into probabilities that sums to 1. Then we sample from this distribution. The most obvious approach is to just pick the highest probability token, call it greedy decoding. But in practice, model uses techniques like temperature to scale the logits before softmax. Like high temperature equals to more randomness and creativity. Low temperature equals to more deterministic and focused. The next thing will be top P, the nucleus sampling. Only sample from top tokens, those probabilities sum to P. And the third thing is top K samples. Only sample from the top K highest probability tokens. So these are some hyperparameters which we use to tune the LLM. The sample token ID gets appended to the sequence. The whole process repeats for the next token. Then the next part is, and this is the crucial part that makes LLM inference uniquely challenging. LLMs generate one token at a time, sequentially. Each token depends on all previous token. You cannot generate token 5 until you have token 1 through token 4. This is called autoregressive generation. The loop looks like this. Take current sequence T1, T2 up to Tn, run full forward pass, sample token Tn plus 1, append it to the list, and then we again loop it through step 1 and up to step 4. This continues until the model generates a special end of sequence token or you hit a maximum length limit. In this, there are two phases. One is prefill and one is decode. So prefill basically processes your entire input prompt, all tokens processed in parallel. This is fast and this is one big matrix operation. In the decode phase, generating the response one token at a time and sequentially. This is the slow part. A 1000 token prompt followed by a 500 token response means one prefill step, that is a fast step, plus 500 decode step, that is the slow and sequential step. This sequential nature is why inference is hard to speed up and why all the technique in this playlist exist. Next we move on is the KV cache, or we can say optimization. So here's an optimization so important. It's enabled by default in every LLM framework. During encoding each step, you are running the full attention computation over all tokens. But most of those tokens were already processed in the previous step. The KV cache stores the key and value matrices from previous step. When you generate the next token, you only need to compute K and V for the new tokens, then concatenate it to the cached version. Without KV cache, we get the like computation time of order of n square work per token generated, and with KV cache we get the time computation of order of n work per token generated. The new token attends to cached KV pairs. This makes decoding dramatically faster. The cost memory for a 70 billion model with long context, the KV cache can take tens of gigabytes. Managing this KV cache efficiently, when to evict, how to compress it, how to share it across, is an entire topic of a different video, and we will discuss that in the future. And finally, completing this video, if I put it all together like what you are about to see in the upcoming videos. So if you see, first there is this user input, which is raw text. Then we tokenize it with the list of token integer IDs. Then we have matrix of word vectors. Then we have this positional in the embedding also. We also apply positional encoding. Then we have this transformer layer, and next we have LLM head to project to vocabulary size, which is 128,000 logits in this case. Next, after that, we will be discussing the softmax and sampling, like which token to choose next. And finally, append the token and go to step 3 for the decode loop. Every video in this playlist is about optimizing one or more of these steps, like attention mechanism, KV cache, quantization, which compresses weights, speculative decoding to speed up the decoding loop, and batching, that is running multiple users through the pipeline simultaneously. Now that you understand the complete inference stack, like on a higher level, this mental model is like a foundation. In the next video, we will go one level deeper into the GPUs itself. We will understand why certain steps are fast, why others are slow, and what memory bandwidth bound actually means in practice. So this was just a high level overview of the LLM inference stack, like what we will discuss in this playlist. Thanks for watching. See you next time.